So from our binomial formula, if P is the probability of success, 1 minus P represents the probability of failure, N represents the number of independent trials, and K represents the number of successes. So our binomial formula is N choose K, N choose K, times P to the K times 1 minus P to the N minus K. If the probability of a severe lung condition for a smoker is 0.3, what is the distribution of number of cases of severe lung condition among 4 randomly chosen friends who smoke? Find the probability where K equals 0, 1, 2, 3, and 4 using the binomial formula for each value of K. So N and P are fixed, right? N equals 4 and P equals 0.3. So the probability that our random number, that our number of severe lung conditions is 0, right? There's only one way that could happen. That is that none of them have a lung condition, which would be 0.7 to the 4th power, which is 0.7 to the 4th is 0.2401. The probability that exactly one of them have a lung condition, right? There are 4 ways that could happen, right? 4 choose 1. Times 0.7 to the 3rd. Those are the 3 that don't have the lung condition. Times 0.3 to the 1. That's the one that does. To the 3rd times 0.3 times 4 is 0.4116. Probability that exactly 2 have lung conditions is 4 choose 2. And 4 choose 2 is 4 factorial over 2 factorial 2 factorial, which is 4 times 3 over 2, which is 6. Times 2 that have the lung condition times 2 that don't. And that's 0.2646. Probability that exactly 3 have the lung condition is 4 choose 3, which is 4, times 0.3 to the 3rd times 0.7. Is 0.756. And the probability that all 4 of them have the lung condition is just 0.3 to the 4th, which is 0.0081. If you add all those probabilities up, you should get 1. All the probabilities should add up to 1. All right. So, probability of a severe lung condition for a smoker is 0.3. Distribution of number of cases is going to look like this. All right, using the binomial formula, N choose K times P to the K times 1 minus P to the N minus K, where N equals 4, P equals 0.3, and K equals 0, 1, 2, 3, or 4. Once probabilities of each value are calculated, a probability histogram can be drawn, right? So 0.24 probability of none of them having a lung condition, 0.41 probability of one of them, and so you just make a histogram of the probabilities. Like any distribution, a binomial distribution has a mean and a standard deviation. The mean of any probability distribution, any random variable, is xi times pi, the value times the probability of that value. The variance is going to be the sum of each xi minus the mean squared times its probability. Fortunately, for binomials, there are shortcut formulas, because doing this all the time would be a huge pain. A 2012 Gallup survey suggests that 26.2% of Americans are obese. Among a random sample of 100 Americans, how many would you expect to be obese? Well, you would expect it to be 100 times 0.262, right? More formally, our mean, mu, is equal to n times p. In this case, n is 100 and p is 0.262. So, the mean is equal to n times p for a binomial distribution. That doesn't mean in every random sample of 100 people, exactly 26.2 will be obese, because that's not even possible. You cannot have 0.2 of a person. In some samples, it's going to be less. In others, it's going to be more. The 26.2 is an average. If we do many, many samples of 100 Americans, on average, 26.2 of them will be obese. How much would we expect this value to vary? That's the standard deviation. And so this is your standard deviation formula. It is beautifully simple. Love this formula. Appreciate this formula. Right? Square root of n times p times 1 minus p. So our n was 100 and our p was 0.262. So the standard deviation is going to be the square root of 100 times 0.262 times 1 minus 0.262, which is 0.738. And you put that into the calculator, and you get the square root of 19.336, which is 4.4 people. All right, so your standard deviation is going to be 4.4 people. On average, our samples are going to vary by 4.4 obese people away from the mean. Mean and standard deviation of a binomial might not always be whole numbers, and that's okay because they are averages. Using the notion that observations that are more than 2 standard deviations away from the mean are considered unusual, and using the mean and standard deviation we just computed, we can calculate a range for the plausible number of obese Americans in a random sample of 100. Right? 2 standard deviations. Standard deviation is 4.4. 2 standard deviations is 8.8. 2 standard deviations above the mean is 35. 2 standard deviations below the mean is 17.4. So if we got a sample of Americans with more than 35 obese people or less than 17.4 obese people, we would consider that to be unusual. And this is a quick and dirty confidence interval, which we'll talk about more, hopefully right before Christmas. I'd like to get into confidence intervals before Christmas. All right, so 13% of Americans think homeschooling provides an excellent education for children. Would a random sample of 1,000 Americans in which 100 share this opinion be considered unusual? So our mean is going to be 0.13 times 1,000, which is going to be 130. Our standard deviation is going to be the square root of 1,000 times 0.13 times 0.87, which is 1,000 times 0.13 times 0.87, which is 10.6. So 2 standard deviations away from the mean is going to be 21.2. So 21.2 above the mean would be 151.2, and 21.2 below the mean would be 108.8. So anything outside of this range would be unusual. 100 is outside of the range, that would be unusual. That would be unusually low. We can also use the z-score, right? Remember, all distributions have a z-score. It's the number minus the mean over the standard deviation. And so that will tell us that it's more than 2 standard deviations below the mean, and that would be considered unusual. Histogram samples from the binomial model where p is 0.1 and we change the number of n. Right? So here, p is 0.1, n is 10. We see this distribution is skewed right. As our n gets bigger, this distribution's a little bit less skewed right. This distribution's pretty symmetrical, and this distribution is very symmetrical, and in fact, very normal. Do note the scales of the histograms are different, right? Here, your mean is 1. Here, your mean is 3. Here, your mean is 10, right? But the shape, look at the shape. So as n gets bigger, the histogram gets more normal. And that is a thing. It's part of the central limit theorem, which we'll talk about more next chapter. So a sample size is considered large enough if the expected number of successes and failures are both at least 10. Right? So if np equals 10 and n1 minus p is at least 10. That is considered big enough for us to approximate using a normal distribution instead of a binomial distribution. So if n is 30 and p is 0.1, then np is only 3. That fails. But when n is 100 and p is 0.1, np is 10, and n1 minus p is 90. That works. And if we go back here, right, the n equals 30 doesn't really look normal, but the n equals 100 does look normal. Four pairs of binomial distribution parameters, which distribution can be approximated by the normal distribution. So np equals 95, n1 minus p is only going to be 5, so that doesn't work. np is 25 times 0.45, which is 11.25, and 1 minus p is 25 times 0.55, which is going to be 13.75. That works. 150 times 0.05, which is our NP, is only going to be 7.5. that doesn't work. And 500 times 0.015 is also going to be 7.5. A recent study found that Facebook users get more than they give. For example, 40% of Facebook users in our sample made a friend request, but 63% received at least one friend request. Users in our sample pressed the like button next to friends' content an average of 14 times, but had their content liked an average of 20 times. Users sent 9 personal messages, but received 12. 12% of users tagged a friend in a photo, but 35% were themselves tagged in a photo. How do we explain this? They have what are called power users who contribute much more content than the typical user. So approximately 25% of Facebook users are considered power users. The same study found the average Facebook user has 245 friends. What's the probability the average Facebook user with 245 friends has 70 or more friends who would be considered power users? Any assumptions we have to make? We have to assume that being a power user is independent, that having friends that are power users doesn't affect being a power user yourself. But we have an N of 245, we have a P of 0.25, and we want the probability that K is greater than 70. We can do this individually, right? That the probability that K is 70 or 71 or 72 or 73 or whatever up to 245. Or we can use the normal approximation. Jazz hands. So we know N and we know P. Our mean is going to be 245 times 0.25, which is 61.25. And our standard deviation is N times P times 1 minus P, square rooted, which is 6.78. And we can use a binomial distribution with this N and this P, or we can approximate it with a normal distribution with this mean and this standard deviation. So remember that your calculator is going to give you the lower end. So we would need to do 1 minus the normal CDF with upper bound of 70, or a lower bound of 70, an upper bound of 1E99, a mean of 61.25, and a standard deviation of 6.78. And if you put that into your calculator, you can also standardize it by getting the z-score and then using so then you could do normal CDF of 1.29, 1E99, a mean of 0, and a standard deviation of 1. And that'll give you the same thing. But at this point, now that we understand z-scores, we can change the mean and the standard deviation and have it calculate the z-score ourselves. So lower bound is 70, upper bound is 1E99, mean is 61.25, and standard deviation is 6.78. And if you try both of those things, you should get the same probability. Ta-da! Binomial distributions.